Hey everyone, and welcome to a very special Digital Foundry interview where we're talking with Intel here about their, I'd say it's a spectacular entry into the dedicated graphics arena. And to begin with, joining us, in addition to our very own Alex Battaglia, of course, there are rays being traced here, he has to be involved. Tom Peterson, nice to see you again.
Thanks, Richard. Great to be here.
And Lisa Pierce.
Hey, Rich.
Hey, fantastic. Thanks for joining us here. I'm going to get straight into the questions. I fully expect you not to want to answer some of them, but we're going to ask them anyway. And but this one should be pretty easy. Obviously, this is a really interesting development from Intel, moving into the dedicated graphics arena. And obviously, it's been a long time in development. You've made no secret of your move here. But what is the overall strategy here? Why are you getting into the dedicated graphics space?
I think, Rich, if you look at it, it's an incredible market. Many of us have been working in integrated graphics for a long time. Intel's been in the graphics business for 2 decades, doing, lower power, constrained form factor solutions. And, the market's hungry, I think, for more options in discrete graphics. So we're super excited to go and enter it. It's definitely one that has big aspirations. With Xe, it's a scalable architecture, not just for client, but also data center. So it's a very interesting time. And I think the industry is looking forward to another player there.
Mm-hmm. Absolutely. Yeah, there has been a sort of convergence in terms of the needs of the markets, right? Because obviously NVIDIA has made a huge impact in terms of AI, ray tracing, and obviously all of this can converge with the gaming market, and it's great to see that Intel is joining the fray as well. So obviously we've had the Alchemist GPU revealed, and I'm going to ask the question that you don't want me to ask, but where do you expect it to land in terms of the overall market here? What is this GPU going to do for gamers? Which is to say, that is my question, which doesn't involve the word performance, but is about performance.
Okay, well, I would say, of course, Richard, we're not going to talk about performance, so I can't directly answer your question. But I can say that, as you walk through what is Alchemist, it is a full-featured gaming GPU first, right? There can be no question in your mind. And it's not an entry-level GPU. It's definitely a competitive GPU. It's got, all the features that are needed for next-generation gaming. So without talking about performance, I'm pretty excited about it.
Fantastic. And it looks like you're going to be first to the market with TSMC 6 nanometer. Interesting choice there. Can you actually quantify the advantages that this process might give you over what's already out on the market and what you'll be going up against in Q1 22?
Well, again, that's getting a little bit too close to performance, but obviously being in the next generation process ahead of other chips gives us an advantage. And there's plenty of experts out there that can give kind of technology roadmap projections, just not this one.
Okay. Here, coming from me, looking at the architecture and all the great slides that you put out. I wasn't able to watch the initial presentation, unfortunately, the other day. Looking at the architecture, we can see there's a focus on rasterization, of course, but ray tracing and machine learning took front center, which is a kind of different strategy, or it's a different strategy than we saw from AMD with its RDNA 2 roadmap, or the way they brought out that GPU series. And it's more akin to what we see from NVIDIA, focusing on machine learning and dedicated ray tracing cores, accelerating things like ray traversal, for example. Intel's going with that kind of approach. How come?
Well, to me, it's just the way that technology is evolving naturally. If you think about AI as being applied literally to every vertical application in the world, for sure it's going to have a major impact on gaming. You can actually get better results than classic results by fusing, sort of an AI style compute to traditional rendering. And I think we're just at the beginning of that technology. Today, it's mostly working on post-rendered pixels, but obviously, I mean, that's not the only place that AI is going to change gaming. So I think that's just a natural evolution. And again, when you think about ray tracing, it's just it delivers a better result than traditional rendering techniques. It doesn't work everywhere, and obviously there's a performance trade-off, but it's just a great technique to improve the life of gamers. So I think that these trends are going to continue to accelerate, and I think it's fantastic that there's some alignment actually, because that alignment between hardware vendors like Intel and NVIDIA and even AMD, that alignment allows the ISVs to see a stable platform of features, and that grows the overall market for games, and that's really what is good for everybody.
Just from an architectural standpoint, I'm curious, why rely on dedicated hardware, for example, for the ray tracing unit instead of repurposing current units that the GPU may already have and relying on just general compute, for example?
Well, the big reason there is because the nature of what's happening when you're doing ray traversal is very different. The algorithms are very different from a traditional multi-pixel per chunk, multiple things in parallel. So think of it as you're trying to find where these rays are intersecting triangles. It's sort of a branching style function, and you just need multiple different style units. So that's really algorithmic. The preference would be, hey, let's run everything on shaders. But the truth is that's inefficient. Although I do know that NVIDIA did make a version of that available for their older GPUs. And you remember the performance difference between the dedicated hardware and the shader? It's dramatic. And it's because the algorithm is very, very different.
Just quickly, one more overall strategy question. Obviously, you've shown one chip, one design, although there was a slide with two chips. I'm assuming the plan is going to be that you'll have a stack, right? You will have different parts. There won't just be one GPU coming out, right? And does the DG1 silicon still have a role to play, or was that just kind of like almost like a test run as such?
Yeah, DG1 was our first step to go and work through a lot of the different, issues and trying to make sure we prepped our stack. It was the first entry there, getting the driver tuned and ready. So, DG1 was very fundamental for us. But really, Alchemist is the start of true, discrete graphics performant GPUs. And there'll be many following it. It was the reason why we shared some of those code names. It's definitely a multi-year approach.
And let's move on to something that's actually just as fundamental to the project as the silicon, which is the software stack, right? This is something where it looks like it's been like an ongoing approach over many years. I guess I first started to take notice of Intel graphics more directly with Ice Lake, and obviously you've come on leaps and bounds since then. Yeah, what is the strategy basically in developing the software stack? Where do you actually want to be when you end up at launch in Q1 2022, and where are you now, and what are the major accomplishments to date?
Well, we've been preparing for XeHPG for some time. And a big part of that is the driver stack having an architecture that can be scalable, from integrated graphics with LP to HPG, and even as you talked about some of the other architectures with HPC as well. And so it's fundamental in the driver design. And it started last year. Last year at Architecture Day, we talked about Monza. It was a big change to our 3D driver stack, really to prepare for that scaling. So that's the first fundamental. Then after that, trying to have the maturity in how we tune for different segments, different performance points, and really squeeze out every aspect of each unique architecture product point. So, within the driver, we've had really four main efforts going on, especially this year, preparing for this launch. The first three are more general. They're not as specific to HPG particularly. So, trying to have local memory optimizations. How well do we use it? What's our memory footprint? Were we putting the right things in local memory for each title? Then, the game load time performance. With the load time this year, it was about 25% average reduction this year. Some are much heavier. The work's continuing, so we have a lot of work to do there, continuing into Q1 for launch. Third was CPU utilization, CPU bound titles. I mentioned on average, we kind of stated things conservatively on 18% on average, some titles like 80% reduction. So that was really the maturity of that Monza stack that we had rolled out and trying to squeeze the performance from that. And then the last one, of course, how well does the driver feed the HPG larger architecture? And so all of these are continuing. It's a constant watch and tuning as new games, new workloads, especially on DX11, DX12, and you'll see that continue through Q1 for the launch.
Because the kind of perception was that when we moved into the era of the low-level APIs, the actual driver optimization from the vendor side would kind of take a backseat to what's happening with the developer. But that hasn't happened, right?
No, it doesn't work that way. It doesn't work that way quite. I mean, the low-level APIs have given a lot more freedom to ISVs, and they've created a lot of really cool technologies. But at the end of the day, a heavy lift is still required by the driver. The compiler alone is just a major contributor to overall frame performances, and that's going to continue to be something that we're going to work on for sure.
Awesome. Not just looking at the latest titles and the latest APIs, does Intel have any plans to increase its performance and compatibility with legacy titles in the early DX11 to pre-DX11 era, perchance?
Yeah, well, our optimization efforts are across. A lot of it's based on the popularity more than anything. So we try to make sure the top titles people are using, that's the highest priority. Of course, there's some heavy DX11, but also DX9 titles. So also based on geographies, it's a different makeup of the most popular titles and APIs that are used. So it is general, but of course, the priority tends to fall heaviest with some of the newer modern APIs. But we still do have even DX9 optimizations going on.
Awesome.
There's a whole class of things that you can do to applications. Think of it as like outside the application, things that you can do to like, hey, you made the compiler faster, you can make the driver faster, but what else can you do, right? There's some really cool things that you can be doing graphically, even treating the game as sort of a black box. And I think of all of that stuff as implicit. It's things that are happening without game developer integration, but there's a lot more stuff that you can do when you start talking about game integration. So I feel like Intel is at that place where we're on both sides. We have some things that we're doing implicit and a lot of things that are explicit.
Okay. In terms of implicit driver functions, for example, does Intel plan to offer more driver features when its HPG line does eventually come out? Because, I've seen it, I've interacted it mainly with it in laptops, or actually as also part of like a Core i9-10900K. But things like, half refresh rate VSync, controllable MSAA, VRS overshading, because I know, Alchemist does support hardware VRS, and it can, use overshading for VR titles. Are there any sort of very specific, interesting things that we should expect for the HPG launch?
There are a lot of interesting features. I think of it as the goodness beyond just being a great graphics driver, right? You need to be a great performance driver and competitive on a perf per watt and actually perf per transistor. You need to have all that. But then you also need to be pushing forward on the features beyond the basic graphic driver. And you'll hear more about that as we get closer to HPG launch. So I say yes. I'm pretty confident.
Okay, so we want to move on to this. This is a topic which came up. We've got a demo showing it in action. It's hugely exciting because we've been massive advocates of machine learning and the applications of machine learning, and it's absolutely fantastic to see a proper competitor to DLSS entering the market that possibly would run across more hardware, which I think is key to its take-up. I'm going to let Alex take point on this because he really is into this and loves to talk about it.
Yeah, sure. Okay, so the first thing I want to ask is kind of what was the drive to make an image reconstruction technique in general from the Intel perspective, and why to make it driven by machine learning processes?
Well, I would say there's a continuum of performance and quality. If you think about you render at low res and you can get high frame rate, or if you render at high res, you tend to get low frame rate. And the question is, can we do better than that? And the answer turns out to be, yeah, if you start thinking about novel ways to reuse information from prior frames or from prior histories of games, you can kind of take in all that other information and use it to reconstruct a better frame. That's really what's happening with all of these AI-based super rendering or super sampling techniques. And at the end of the day, it's hard work. It is, don't get me wrong, it's rocket science, and we have some of the best AI people in the world working on it, but the results speak for themselves. You can actually get a better result by either, interpolating or sort of say integrating information across multiple frames and then adding onto that information that can be trained into a neural network from looking at, millions or hundreds of frames from other games. It's really just a spectacular technology.
So it seems the way you're describing it there, that there is a large training process in the background based upon perhaps highly super sampled images of certain games. and then the inference based upon the weights generated from that are done in real time on the GPU.
Yeah, of course. And we have, of course, multiple flavors of that inference. But the cool part is that they're generic in the sense that they're not trained on a specific title. The inference works across multiple games because at the end of the day, they're all very, very similar. And I think of it as it's almost the best of the world, where you can kind of say, take this engine, train it on a bunch of data that's from different games, and then use that across multiple different titles to get great results.
Okay, kind of talking about the different inferences and the paths you mentioned there. The presentation specifically mentioned the XMX path as well as the DP4A one. Could you perhaps go into more detail there about which ones are specific to the Intel architecture and which ones aren't, as well as perhaps differences in performance and perceptual image quality that each one might have on Intel architecture?
Jesus, is that the only question you have? We're gonna roll it all into one question.
Okay,
We could be here all day, honestly.
I'm just
All right,
excited.
So to start off with, let's. I got to back up. Okay, you're gonna
Okay.
on for a second. So the truth is, people confuse all these rendering techniques and post-render techniques, and they kind of blend them all together into imagery gets better. But there are some really different things going on in general. There's something that I think of as upscaling, or sometimes people call it super resolution. And what you're doing there is you're taking a low resolution image from a single frame, and you're kind of blowing it up using multiple different techniques. And that is a very high performance technique that gives you an okay result in many cases, but it's not like, it doesn't have all the information available to it. It doesn't know about prior rendered frames, and it doesn't know about motion vectors, and it doesn't really know about the history of all frames that have ever been generated. So if you compare that upscaling technique, or upsampling, or I think upscaling is a better word, you compare that technology to what's happening with something like XeSS. In XeSS, we're taking multiple frames of the game, and we're looking at motion vectors, and we're also looking at prior rendered frames that have been trained into a network. So effectively, we're looking at a lot more information to generate that new frame that kind of has a better characteristic than traditional upscaling. Now, when you think about how do you run that XeSS algorithm, the initial ones we've talked about are the XMX engines, which are systolic. That's kind of the traditional method of doing fast inference on a GPU. And the other method is DP4A, which is another kind of simpler form that can be more broadly adopted across multiple different architectures. So I think of it as on hardware platforms from Intel that support the core engine, we expect to make XeSS available on that device, right? So that's pretty cool, right? You kind of say we have multiple backends that all plug in underneath a common API. And that is, to me, the most important thing, is that ISVs are looking for these common APIs. So they can do one integration, and then underneath that integration, you could have multiple implementations of the engine without sort of ISVs having to reintegrate and reevaluate every time. So our expectation is that that's exactly what XeSS is. It has a standardized API that could even work across multiple vendors. And so part of the key strategy of XeSS is to be open. Let's get these APIs out there, and let's let other people, implement underneath these, so that we can make the life of ISVs a little bit easier. And over time, the hope is that this kind of stuff will, of course, move up higher into cross-industry standardized APIs, but all that stuff takes time. So what we're kind of thinking is, hey, let's get our first version out there, make it awesome, then publish it, kind of make the APIs open, and then over time it gets standardized.
That kind of precedes my next question. Thank you so much. As a part of that, you said your own SDK, your own API out there that may eventually trickle down or trickle upwards into something more broadly standardized. Is the first iteration actually using Microsoft's DirectML at all as a part of it? Okay.
No. Now, there's a good question about that. Why not? And is the API, are the Microsoft APIs becoming more so that we could just use those? The truth is, we have our own internal programming language that we're using for the high performance kernels that are part of the implementation of XeSS. And all that stuff right now is very Intel in kitchen, kind of super optimized Fuse kernels, like beautiful, almost like a dude is like, you remember like coding in assembly from back in the day? I can imagine like Richard with a tiny little ball cap doing the assembly code. We have like a whole crew of those people making XeSS just perfect. So that's where we are today. But over time, as say Microsoft's APIs for shaders extend, maybe this whole thing can just become shader based. But it's not a shader based traditional shader. It's shaders that are optimized for sort of the XMX style architecture.
Okay.
Yeah, just for the record, Tom, I checked out on 6502. That's how old we're talking here.
I see.
But, I guess the sort of more nuts and bolts question. In your demo, you were showing a 1080p scaled via XeSS to 4K. Will you be supporting different internal resolutions? Is that a sort of tweakable there?
Yeah, I think you'll see XeSS will support multiple different configurations. There's like a quality mode, a performance mode, and different input resolutions to different output resolutions. I'm not sure what that cross matrix is going to look like right now, but there's no need for this to be just one in, one out.
Okay, right, got it. And the sort of SDK side of things, I mean, all of these features kind of live and die by actually getting implemented in titles, right? So it is basically, I mean, how open is open? Are we talking about like source code on GitHub or something more akin to what NVIDIA did with the DLSS SDK?
So the way to think about it is it's definitely in everybody's interest to have open ISV APIs. And what that means is we literally the same API, everybody integrates that, and underneath it you plug in sort of different DLLs that implement the engines basically that are implementing the features. That's going to take some time, right? So in the short term, what we'll probably be doing, and I think there's still a little bit of motion here, is publish the APIs, publish the SDKs, and publish references and then effectively ISVs will know what they're getting. And there's really nothing about that feels awkward to me. Over time, you'd like to be even more open, where these, there's APIs that people can plug in underneath them, and that's effectively the strategy. Now, we'll still very likely have our own internal engines that plug underneath these APIs, and over time, whether those are going to be open or not is not clear.
So is there actually a sort of limitation on which GPUs from other vendors will run it? I mean, I'm assuming there has to be some kind of machine learning acceleration involved, right?
That's really a question for other vendors, right? You've seen machine learning style applications run on GPUs with none, right? There's no reason it has to have a particular hardware. It's just a performance, quality kind of complexity trade-off.
Yeah,
absolutely. So here's an interesting thought that I had during the architecture day, which is that essentially you do have machine learning silicon, not just in the GPU, but also in the CPU. So let's say I own an older GeForce or Radeon card, and I want to tap into XeSS. Can I do that via the CPU?
Well, you know that there's an integrated GPU on most of our CPUs. And so the question is, what would it look like? And I'm sure, Richard, you're aware of like how hybrid works for most notebooks, where there's a discrete GPU render, and then there's a copy to an integrated GPU that today does nothing other than act as a display controller, really. But now that we have technologies that are really cool post, could we do something interesting on the iGPU? I think that entire space we call deep link. And what happens in terms of deep link right now is we're still learning so much here, and there's so many opportunities. And I don't think of deep link as, I mean, today it's just Intel products working together, but you can think about deep link as just like, what can we do in a 2 GPU environment or in a CPU GPU environment that's better than otherwise. So I don't want to answer that question directly, but let's just say there's lots of opportunity in that space.
Mm-hmm. I mean, because fundamentally from an Intel point of view, if you're able to address machine learning silicon, does it fundamentally matter if it's on the CPU or the GPU? That's kind of the question I've been pondering.
It's the performance, it's the perf per watt kind of, is the compute in the right place to affect the pixels that are moving through the pipeline. So there's no religion about it. It's just like, what's the science lead us to? Do we have a feature that's going to deliver benefits to customers? And if we do, we'll do it probably. I mean, there will be no hesitation if we find a great technology that makes our CPUs deliver a better experience than somebody else's.
Just another quick question here regarding the ray tracing setup on these GPUs here, or on this GPU architecture. It does have a dedicated ray tracing block, accelerates multiple things. It is outside the main core area, it looks like. Can it actually run concurrently with the normal vector engines or XMX engines to further increase utilization, saturation, or just GPU parallelism working the most at the same time?
I unfortunately don't know the answer to that. I think yes, but I would want to double check on that.
Okay.
That's an excellent question, though. Stump the host. Good job.
Obviously, there's a lot of fantastic technologies that were sort of released and talked about at the Architecture Day. And obviously, at the end, there was the moonshot, the Ponte Vecchio. And obviously, this is a completely different area to what we're talking about in terms of mainstream consumer graphics. However, principles-wise, you were showing scalability on a multi-chip level, right? You were bringing multiple GPUs together, and from the looks of it, in terms of how they're linked, they seem to act as one coherent whole. Now, obviously, in the gaming space, the concept of bringing together multiple GPUs together and to accelerate performance kind of died with SLI. It didn't really scale to modern architectures, to temporal applications specifically. My question here is, looking to the future, that technology, that could scale down to the consumer level, right?
Well, again, I don't want to talk anything about unreleased products, but I can say that, there is this. Let's back up to Ponte Vecchio. The target of Ponte Vecchio is compute, right? And compute scales very easily, very naturally. And having multiple compute die across a giant workload is just a very straightforward scaling process. It's not there's not like a heavy software like mapping thing that has to happen. It's very much the way the problem is defined with super, kind of supercomputer loads. That's very different on consumer. Really what killed SLI, or I don't know how, I guess I'll give you my sense of from the outside about what's made SLI difficult, is the multi-frame nature of SLI, where you're kind of trying to say AFR is the technology they use. And the idea is they render one frame in each GPU that's temporally separated, and then they're just going to display them in time. That technique breaks down with modern titles because of post-processing and frame-to-frame kind of cross communication. So, to do it on consumer, we would need a new technology, a new way of partitioning work across multiple tiles. And the degree to which there's high bandwidth communication across that tile, you can kind of ignore the fact that they are multiple tiles. Like if they had infinite bandwidth between tiles, they just look like a big piece of silicon, and there's no software visible behavior. Now, there's not going to be infinite bandwidth, so there's going to be some kind of work to do that scaling across tiles. But I think that's the trend. I mean, if you just look at how silicon works and you look at how yield works, having multiple smaller die over time is probably a very good idea, and that would need to be made to work somehow. It's not going to be anything like SLI. SLI is a technology that worked great with DX9 and DX11. It's going to be something different, I think.
Mm-hmm. Okay. One final question from me. It's a bit more global, and it is essentially about relationships with developers, right? Because this is just as fundamental to getting good performance as the silicon, as the driver. You actually have to kind of be there with the developer to help them to optimize for specific architectures, right? What is Intel's vision there? How are you deploying that sort of idea?
We've had a deep engagement with the gaming ICs for a long time across Intel, right? But now it's at a point of a much deeper engineering engagement, and it's been building last 2 years. We know it's critical table stakes for success in high performance consumer graphics. So it's been building stronger and stronger, getting more capable tools, more capable SDKs, and bringing them along to help make sure that we have the best possible experience for gaming, on Alchemist and in the next few years and the new features. So we'd expect, ultimately far more than day zero driver alignment, upfront tuning, upfront engagement, maybe some unique optimizations that we can go and drive in even before it's in the final stage for launch. So, we view those relationships absolutely critical to the future of discrete graphics.
Okay, there's also been a drive to increase functionality kind of adjacent to gaming, not specific to gaming, for example, streaming. How are things going there, and what are the plans for the future?
In streaming, this is one of the cases where we really see Deep Link as an interesting technology for us to continue to improve on. It's always great when we have integrated and discrete graphics on the system. Capture and streaming is one of them. our encoders have been a strong point for some time. How do we make sure we leverage the balance of high performance, what quality levels we want? There'll be a lot of distinct solutions we want to bring there, and we'll see more and more about that with the Alchemist launch.
Fantastic. You have any further questions there, Alex?
This is a little bonus question regarding the difference between the HPG and HPC setup. I noticed that the EU is quite a bit wider, like 2 times as wide in the HPC arena. What is the design decision for that and not to use that in the high performance graphics setup?
Well, it's all about the segment that they're targeting. Obviously, there's some parallelism that's more prevalent in the workloads at different segments, and I would attribute most of the architectural difference to the workloads that the architecture's tuned for.
Okay. Well, thank you very much.
I think we're good here. I think my sort of one remaining question would be, again, returning to machine learning. Basically, it's the new frontier, right? This is where the possibilities are endless. But what is the next possibility? Obviously, super sampling is the big one at the moment, but it's just one opportunity, right? Do you have any thoughts on where things are going to be going in the gaming arena?
I have a million thoughts. That's what I do. What are you talking about? But I don't want to talk about them, Richard. But I can tell you a few things that I think are super, and I can talk about them because it's just straightforward to me. Right now, we're working on post-rendered pixels. And post-rendered pixels, you've kind of left a lot of the information already earlier in the pipeline. And so the question is this idea of fusing more information from deeper, back, or maybe even start taking a look at like, hey, what about physics engines? And what about all of the other engines that are feeding into the render, like projection and geometry kind of expansion? So there's just many algorithms that are running that are prior to pixels. And all of those are candidates for feeding into some kind of generative algorithm, which is really what AI is all about. Imagine, AI kind of does 2 things. One is it does, think of it as extrapolation, where it says there's information here, I'm just going to move it forward in some kind of reasonable way. But it also does hallucination, where you kind of say, I've seen things in the past that are like this. So wouldn't it be great if there was a tree here? This is what AI does. And so all of that stuff is perfect for games. And there's many different applications.
I look forward to seeing that explored, definitely.
Same.
But fundamentally, just thanks so much for answering all of our questions here.
Yeah, thank you very much.
Pleasure.
So really great to see you. And you both look like you're doing great.
Yeah, fair to middling, but hey, this isn't really about us, it's about you. And just to reiterate there, I really thought the Architecture Day stuff was fascinating. Great stuff happening on the CPU side. Really looking forward to testing Alder Lake. And as for Intel Arc, the GPU side of things, hugely exciting stuff. Can't wait to get hands-on with the hardware. But that's all from us for now. Thanks again to Tom and Lisa for joining us on this one, and of course Alex Battaglia. But yeah, please do like, subscribe, share, ring the bell for instant notifications whenever we post new content. But that's all from us for now. Thanks for watching.